Okay, so we started with this function, with this equation. We're going to call f of t the driving function. We're going to call x the response function. We've got a system that we talked about, and we drive it with some function and see if we can measure the response function. If we can do that, well, then we can determine what the system transfer function is. System transfer function, okay, we solve the equation, we get this, we make the simplifying assumption systems at rest in stable equilibrium, and we get the Laplace transform of the response function equals the Laplace transform of the driving function divided by something that looks a whole lot like the characteristic equation that we would get if we were solving the homogeneous equation. We define phi of s to be reciprocal of this denominator, so that phi of s times Laplace transform of the driving function equals Laplace transform of the response function. And now the payoff is the system transfer function can be obtained by actually driving the system and observing the response function and taking its Laplace transform and dividing by the Laplace transform of the driving function. Usually we use a simple driving function. Okay? And we can do that for any driving function we want to use. If we get the response function, we can calculate the Laplace transform, we know the system transfer function. And then the thing we get out of that, if we know the system transfer function, well, that function is this. We can identify m, gamma, and k. So we know what the parameters of our system are. We know the mass, the drag coefficient, and the restoring force constant, which is a big deal. Okay, so if we have, this is just out of the textbook, driving function t, response function, I'm not going to read it to you, there it is. We can easily do the Laplace transform. One hang-up was I used h of t here. -2, or 2 times -1 is -2. We've got a function that's -2 for t greater than 0. Well, the Heaviside function is 1 for t greater than or equal to 0. So this is -2 times the Heaviside function. Okay? And the Laplace transform of the Heaviside function is just 1 over s. So where'd it go? -2 over s, right? Comes from this. And then the rest of these are very straightforward. You have very straightforward formulas. You can figure any of these out by integration. And as I say, I'll probably ask you to figure something out by integration. Because you've got to know what to do if your table doesn't tell you what. Although if you got a good table, well, if you don't know how to read the table, you're going to have to do an integral. Okay. Okay, so now, so we're easily going to get our phi of s. Okay. Going to be the response function divided by the driving function. Well, that's going to be the reciprocal of the driving function is s squared. Okay? And that's going to be times 2 over s plus 1. I'm reading here, I should be reading here. I'm going to leave it the way it is. 1 over s plus 1 squared minus 2 over s plus 1 over s squared. Okay? Now I'm multiplying through by s squared, so that's going to give me 2s squared over s plus 1 plus s squared over s plus 1 squared plus 1 minus 2s. Now we put that over common denominator s plus 1 squared. We get s squared plus 2s squared times s plus 1 squared minus 2s times s plus 1 squared. And then I got another term. Plus this all over s plus 1 squared, and that's getting hard to read. And I'm just putting all this over common denominator. And just looking at the time, not sure I want to actually finish this. Anyhow, you can finish this. Okay? That'll be your system transfer function. Make sense? It's going to be a cubic polynomial on top. It's going to be s1 squared at the bottom. Something about that doesn't look right. It's the wrong degree. It should be something else, because what I'm getting doesn't look like something that's particularly easy to inverse transform. I mean, you do it. Anyhow, this is the process. Okay? So, I'll do another video and finish it out. But the process is actually, pretty simple. And once you have the system transfer function, you could apply it to another driving function. I still have to inverse transform your result. But the other thing is you get the parameters of your system.